reason they gave for not funding was that we hadn't explained in our proposal how we were going to choose the lecturers and the students to have better representation of otherwise underrepresented minorities. We waited to submit the proposal until we actually had lined up all of the lecturers. And of course, our main criterion was the very best possible lecturers. But I think that the lecturers and students are a pretty diverse group. In any case, rather than giving the explanation for how we chose them, we just gave them a complete list. Anyway, sorry about that. We do have some money in the budget from the University of California that can be used to cover your travel expenses. But I was hoping that we would have enough from the National Science Foundation to cover a large fraction. And unless we can get it first, that won't be the case. So today, I'm going to continue from last time, and this time talk much more about simulating galaxies in the universe. The great simulation of the large-scale structure in the universe and dark matter halos of galaxies is the Millennium simulation. It set a new standard. It was the benchmark. It's been the source of more than 400 papers. It's been used to study properties of halos, evolution of the number density of halos, evolution of distribution and clustering of halos, accretion history of halos, halo statistics of all kinds, void statistics, the quantitative description of the evolving cosmic web, merger trees, which are essential for semi-analytic modeling, more on that later. And it has many, many virtues, but a significant flaw. The problem is that it was based on determination of cosmological parameters that was insecure, too early. There wasn't a lot of choice. They must have started the simulation in 2004. And the best determination at the time was the 2003 first-year data release from the Wilkinson Microdynamics probe, combined in the new paper by David Spergel et al. With other available data. But as you see, the WMAP alone data had huge error bars, sigma 8.90 plus or minus 0.10. The Millennium choice had a somewhat lower than their favored value for omega matter, but that turned out actually to be. Anyway, the 3-year data release of WMAP was inconsistent at the 1 plus 1 sigma level. Maybe they barely consistent with their first cut. And then the 5-year data release and the 7-year data release in 2010 essentially have converged. And as you see, they're somewhere in between the WMAP 1 and WMAP 3. Meanwhile, a lot of other data has become available. And this is a summary of data from several different sources. The black solid curve and the black dash curves are X-ray cluster studies. The number of nearby clusters as a function of mass, the evolution of the number density of clusters with Redshift are both powerful probes. And the gray region is from the Sloan survey. So this is the Sloan optical clusters combined with gravitational lensing data. So as you see, they're remarkably consistent. The error bars are always 1 6. Moreover, they're extremely consistent with the WMAP 5 and WMAP 7. So the black, the green here, this dot, was the parameters that we chose when we started the Bolshoi simulation in 2009. And those are extremely consistent with all current data. They're consistent with WMAP 7. They're actually closer to WMAP 7 than to WMAP 5. So the problem is that Millennium is about 4 sigma away from the current best observational constraints. 4 sigma away just in sigma 8, for example, which is the normalization of the power spectrum. Technically, sigma 8 is the linear mass excess, or delta m over m, on a scale of 8 H inverse megaparsecs. So it's the RMS fluctuation on that scale, basically the cluster scale. In any case, you can use that to normalize the fluctuation amplitude. And the fluctuation amplitude used for millennium is too high. So this is a sort of brief summary of the Bolshoi simulation. The millennium simulation used Volker Sprengel's gadget code, the particle function code. The Bolshoi simulation also used the particle-based code, but it's an adaptive mesh code, Clifton's adaptive refinement tree or R. We found to be somewhat more efficient than gadget, trying to get very high resolution, high spatial resolution. It has 8.6 billion particles. That's 2048 particles. It has a kiloparsec force resolution. That is to say that that's where we stopped allowing it to keep resolving. So the deal was that if 5 particles or more end up in a cell, we break the cell up into 8 smaller cells. And we keep doing that until we get down to a cell of size 1 H inverse kiloparsec. A box of 250 H inverse megaparsec. So the dynamic range is 200,000. Of course, you can't allow particles across the smallest cell, the time step for that cell. So on a small scale, there are 400,000 time steps. It took about 6 million CPU hours. It actually took over 10 million, but we were doing the simulation as they were building the NASA Ames. We lost lots of data. Helped them find problems in their machines for a while. And if you just add up what was actually used, about 6 million CPU hours, we were using 14,000 cores for the whole calculation and 12 terabytes of RAM. It ended up with about 75 terabytes of disk storage for all the time steps. We stored positions and velocities and an identifier for every particle at 100 time steps. So the cosmological parameters are consistent with the latest observations. Force and mass resolution is nearly an order of magnitude better than Millennium 1. Force resolution is the same as Millennium 2, but the volume is 16 times larger, so we have much better statistics. Our mass resolution is not as good as Millennium 2. So, but they had only 100 H inverse megaparsec box. Halo finding is complete to around 50 kilometers per second circular velocity, using both Clifton's EDM and also Peter Baruzzi's Rockstar Halo Finder. Peter's going to be here later today, and you'll learn more about that from Peter. Bolshoi and multi-dark Halo catalogs. Multi-dark is a bigger simulation I'll tell you about in a minute. They were released in September 2011 at the Astronomische Institute Potsdam, and the merger trees will be available here. Peter Baruzzi has constructed the merger trees, both Halo sets, and more about the merger trees. Gerard Lemson, who created the Millennium database, was extremely helpful in creating the database, the searchable database for Bolshoi. Well, and you'll hear much more about this from Gerard. So this is one of the highlights from our first paper, the basic summary of the Bolshoi simulation. So for many years, we've been using approximations to Jenkins or Shefton Torman to describe the abundance of halos as a function of their mass. And the curves represent the Torman function for the cosmological parameters that we use for Bolshoi. And as you see, at redshift 0, it's an extremely good fit. But at redshift 10, it's off by a factor of 10, over-predicting the abundance of halos by 10 times, essentially independent of mass. Now, the reason is largely, but not entirely, that the halo finding that was used for Shefton-Torman, fitting that to earlier simulation, was friends with friends, where basically you take a linking length, typically typically about 20% of the average interparticle spacing. And then you say all the particles that are linked together, that is, that are within that distance of the particles, are a halo, which is basically defining a sort of minimum surface density. Now, if halos are well organized, that is, dense centers, low density, lower density as you go out, then it's going to give very similar results to other halo binders. So that's why at Redshift 0, it's basically giving the same results that we got. We're using a bound density maximum halo binder when we did this. So what we're doing is searching in spheres starting at the highest density points, and then throwing out unbound particles and refitting and converging in prize. And that's how that method works. At high redshift, they diverge drastically. The friends of friends versus vertical overdensity method. And this is from an appendix of our paper, and it illustrates the problem. So in each one of these figures, there's one halo at the center, which is identified by the bound density method. But all of the halos that are circled in color are friends of friends halos. I have it exactly backwards. All the circled ones are the bound halos. All of those were linked together as a single halo by friends of friends. So in the upper right corner, upper left corner, we give the ratio of the friends of friends mass to the spherical overdensity mass. And as you see, it's typically around 3. Now, the consequence of this is that spherical overdensity is systematically overestimating the mass of halos at high redshift. And so the result is that the mass is high by about a factor of 2.5 or 3. If you go up by that factor in mass, you're going to be predicting the abundance of halos by about a factor of 10, because the abundance falls so steeply as a function of mass. Anyway, for people who are worried about having enough galaxies to reionize the universe, clearly the galaxies are going to form in these gravitationally bound spherical overdensity halos, not in friends of friends halos. So we ran another simulation after Bolshoi was finished. We get good statistics on clusters. So this simulation is in a 4 times larger volume, 4 times larger size volume. That is, instead of 250 h-inverse megaparsecs, it's 1,000 h-inverse megaparsecs or gigaparsec on a side, which is about 4 billion light years. And it's exactly the same cosmology, and the resolution was 7 kiloparsecs. And here we found it was about 170 kilometers per second, so it would barely find Milky Way mass halos, and halos more massive than that it would find. So the volume is 64 times larger than Bolshoi. So this combination gave us what we thought was a very good way to characterize clusters on the big scale, galaxies on the scale of Bolshoi. Incidentally, I should explain that before we ran this, we spent a lot of time figuring out what the right parameters would be that would be consistent with the amount of computer time that we had, which is around 10 million CPU hours per year, and would be very useful for a lot of purposes, mainly to get the merger trees, which are going to be the basis for semi-analytic modeling and various other ways of filling these galaxies, filling these halos with galaxies. So this is the paper that reports the results from big Bolshoi or multi-DART. It's the same simulation. There's a Spanish grant called multi-DART, which was used to cover some of the costs of creating the database. And so the Europeans like to call it multi-DART. So this is by Paco Prada et al. And one of the highlights of that paper was to correct an incorrect statement in an earlier paper by Macho, Dutton, and Van den Bosch, who had claimed to do a calculation for the same cosmological parameters and said that it was drastically in disagreement with the observed concentrations from X-ray studies mainly of cluster size halos. And so this is one big survey of clusters, all the black points with their error bars. This is the median as a function of halo mass. Concentration is by definition using the Navarro-Frank-White formula for density basically 1 over r at low density, 1 over r cubed at high density, at high radius, 1 over r at low radius, switching over to 1 over r cubed at high radius around the center of the halo, with the division point where it switches over, called r sub s, the scale radius. You divide the radius of the object by the scale radius, and that's called the concentration. There are 2 radii that are used for the object. 200 times critical density, that's often called R200, or what's called the virial density. And all of our catalogs for Bolshoi, big Bolshoi, calculate both ways. So some people like R200, fine. Some people like virial, fine. All the calculations are done both ways, so take your pick. They're all there. We're trying to make this as usable as possible. The red point is the summary of the results from another big X-ray cluster survey. And the point is that it's very consistent with the results from big Bolshoi. The upper dash and lower dash lines are the 90% value. This is the macho prediction. You see what the problem was. It's in disagreement with this summary of a lot of data by, I don't know, 3.5 or something. Which would have been very bad, except it wasn't right. It was a small simulation, and we don't know. But I talked to all 3 of the authors. They basically threw up their hands and said, we don't know what the problem was, but they all agree that it's reliable. So you can make these kinds of pie diagrams, and this particular one was done by Risa Wexler and Rolf Kahler. Thank you very much. And Nina McCurdy actually made this figure. Made for this article that I mentioned yesterday in the current issue of Science Telescope magazine. I like these kinds of things. They're not particularly useful. But anyway, you're supposed to see that the simulation looks a lot like the real universe. Of course, to really test this, you have to do much more detailed studies, like looking at the point correlation function of galaxies of different luminosity that are fit into halos, either by abundance matching methods or by analytic modeling. And I'm sure that Risa Wexler and Darren Krogner are going to tell you much more about that. So I'm not going to spend a lot of time on it, but the bottom line is that the agreement is extremely good with the observation. Now, the merger tree is a crucial thing. You have to find every halo that merges and merges and merges and merges to make a halo at the end of the simulation. You want to fill the halos either by an abundance matching method, or especially if you want to follow the evolution of a whole population of galaxies using the semi-analytic modeling method. You must know the complete merging history of every halo. That's called the merger tree. So Peter Baruzzi developed a wonderful new method for doing this, which, as far as I know, is a great improvement over anything that's ever existed before. Fortunately, we were able to use that for Bolshoi. So the idea of the method is that the problem is that you lose halos both at the edge of detectability, in other words, where you're beginning to be incomplete, and also when halos cross other halos. There's a problem of definition. Is it 2 separate halos? Often a halo will go through another halo and they'll separate, and then they'll come back together or whatever. And so there is that definition problem, and then also the incompleteness problem. And what Peter's method does, so he did 2 wonderful things. One is he created a wonderful way of finding halos, which is a 6-dimensional adaptive method. That is, it basically in low density regions where halos tend to be isolated, it just is basically a friends of friends method. But it's adaptive, so it looks to see what the local density is, and then uses its linking, determines its linking length based on that. But in high density regions, it goes over to a 6-dimensional method where it's also using the velocities as well as the positions of every particle. So it's extremely efficient at finding halos, even in very dense regions, but it doesn't waste time using the 6-dimensional method until it has to. So it's also publicly available and quite easy to use. Now, let me just show you this one again. This is the merger tree of a single big halo. There it is. Now, remember, we're using spherical overdensity method, so every one of the halos is going halo spherical. And the size is the radius of the halo. So every one of these little halos has some high redshift, and you can read the redshift, it's listed here. We're starting at something like redshift 8. Every one of these is going to become a subhalo of the final big halo. And if you look carefully, you can see that there's basically 3 filaments that are crossing at the point where this big halo is forming. And so the objects are moving in, moving in, moving in. Once they become subhalos, they're still being tracked, but this picture isn't showing them. Now, the halo catalog and the merger tree are like half a terabyte of data. The entire, for all redshift, the entire catalog of all the points is about 75 terabytes. So the total, is, if you add in all the other information that we're collecting about all these halos, shapes, momentum, etc., it's less than 80 terabytes. That's the sort of magnitude. Now, using the merger tree data, one of the things that you can do is halo abundance matching. And what we did in this paper, which was led by Sebastian Trujillo Gomez and Analytic graduate student, was to match up, to rank order galaxies by, in the Sloan survey, by red band luminosity. The halos are rank ordered by their peak circular velocity. So at any given time step, a halo has a circular velocity defined as the square root of Newton's constant times the mass enclosed by radius r divided by radius r. The maximum of that is called Vmax. That's the maximum circular velocity. For an NFW halo, that occurs at 2.15 times r sub s. R sub s being the scale radius. Over 1 over r to 1 over r cubed. For any halo, it's going to be somewhere around there. But NFW is pretty good. So the peak circular velocity is the maximum circular velocity as you go back along the main tree of any particular halo. So in other words, that halo, if it's an isolated halo, will have a peak circular velocity which is probably very close to its maximum circular velocity. With a subhalo, however, it is going to start getting stripped. Being inside a bigger halo, the gravity of the bigger halo is going to be pulling off the particles, the less bound particles. And so its maximum circular velocity is going to go down. The idea is that the galaxy that formed in that now subhalo is going to be determined by the circular velocity, the maximum circular velocity that it reached along its trajectory before it became a subhalo. So that's why I wanted to show you this picture that shows you how halos, many, many, many halos become subhalos. So thousands of galaxies of all different sizes would be in that big cluster halo. And of course, we're tracking them. And we're actually going to continue to track the locations of them, except we'll lose some as they get stripped too much. But the galaxies should all still be there. Well, some might be completely destroyed, but most of them will still be there. Anyway, so the rule then was to line up the halos by peak circular velocity, the galaxies by basically something that's supposed to correlate reasonably well with the mass of the stars in the galaxy, the R-band luminosity, and then match them up so that you have roughly the same number density of objects. That's halo abundance. Or as Risa likes to call it, somewhat more modestly, subhalo abundance matching with the abbreviation SHAM. Because of course it's not the real universe, it's a trick. She'll talk much more about that because she's done a lot of work on how good it is and what the problems are. In any case, if you do that, you then have assigned the luminosity to every halo. So you can ask, how well does this agree with the well-known luminosity-velocity relations for galaxies, namely the Tully-Fisher relation for disk galaxies and the Faber-Jackson relation for elliptical galaxies. And in order to do this, we found that there wasn't really a good summary of the early type or elliptical type galaxies that are mainly toroidal. So working with Aaron Romanowski, we created a reasonably good catalog, the best we could do. The brown points are the early type galaxies, that is spheroid dominated. The blue points are the disk-dominated galaxies. And the two different curves up here represent whether you include adiabatic contraction of the dark matter halo or not. The higher curve is with adiabatic contraction. So the idea is that when the gas cools and falls to the center of the halo and forms stars there, that's going to pull in some dark matter. And an early calculation of that was by Blumenthal, Faber, Flores, and me in 1986. And that's the formula that we used, which probably somewhat overstates the effect, the extent of this effect. So the idea was that we wanted to bound the two. So we either didn't include the effect or we did include the effect. We always include the baryonic, the cold baryons, that is the stars and the cold gas that ends up in the center of the halo in calculating the circular velocity. We had a simple method for doing that, which is going to be pretty good except for the most massive galaxies. But in any case, our point in this figure is that the truth seems to be consistent, I mean, the observations seem to be consistent with something between these two. And interestingly, the early type galaxies really seem to need the adiabatic contraction, whereas the disk galaxies don't seem to. And that's a conclusion that other people have reached, especially Aaron Dutton and collaborators. There's another similar relation between the baryonic mass of halos and the velocity. So instead of on the vertical axis having luminosity, this time it's baryonic mass, and pretty good agreement. Here, what we did was to take the Sloan survey, and for the low mass, the less luminous galaxies, the radio survey that was available when we wrote the paper, which is the HiPACC survey from Australia. But the alfalfa results, that's the preliminary results from the upgraded Arecibo telescope, looking at distant galaxies 100 megaparsecs and more, is quite consistent with HiPACC. So what this shows is calculating it both ways, with adiabatic contraction, without adiabatic contraction, the red curve and the green dash curve. And the purple curve is the data. So this is Sloan, this part is HiPACC plus Sloan. And it's very consistent. And what you're supposed to learn from this is between about 100 kilometers a second and as high as galaxies go, 350, 400 kilometers a second. It's quite an acceptable match. That is, the velocity function of the halos and the velocity function of the real galaxies seems to be good agreement. However, at 80 kilometers a second, there's a factor of 2 discrepancy. At 50 kilometers a second, it's a factor of 10. That is, the simulation is predicting a lot more halos than we see galaxies. This could be a very serious problem for cold dark matter. That was lambda CDM, which is what we assume here, cosmological constant plus cold dark matter. Might indicate a need for warm dark matter or dark matter interactions or something that suppresses the number of halos. Or it could just be incompleteness. That is, these shallow radio surveys are just not finding enough high velocity objects. It could be, in fact, they're finding many of the objects, but they're not seeing the rotation curve go out far enough to actually pick up where the velocity plateauing. So, which is it? And the answer is we don't know yet, but here's a tantalizing new piece of data that was presented at a conference in Santa Barbara at the Institute for Theoretical Physics in February of this year by Anatoly Klipin, who's been working with Kara Chentsev at the Russian 6-meter telescope. And what they're finding is that at 80 kilometers a second, so this is a very deep survey. It's trying to find every object that can be seen from that observatory in the northern hemisphere out to 10 megaparsecs away. And they really went very faint. And so the conclusion is that at 80 kilometers a second, there's no discrepancy. At 50 kilometers a second, at 40 kilometers a second, the discrepancy is only a factor of 2. And at 40 kilometers a second, there are all kinds of physical processes: reionization, squelching, the effect of supernovae, that should drastically decrease the success in forming visible galaxies, either objects with gas or objects with stars, at these low velocities, objects that we'll be able to see with telescopes. So this is not published yet, but the preliminary results are certainly very favorable to cold dark matter. So keep an eye out for this paper. Another way to test whether the simulation agrees well with observations is to look at the abundance of satellites. So this is a picture of the Milky Way galaxy based on the published picture and then modified a little bit by McCurdy and adding the actual optical images of the large and small Magellanic Clouds. So the question is, how common is it to have a galaxy as bright as the Milky Way with 2 satellite galaxies as bright as the large and small Magellanic Clouds? Now, the large and small Magellanic Clouds have circular velocities of something like 80 or 90 kilometers a second and 60 or 70 kilometers a second, well above our completeness limit. So Bolshoi should have every single halo of this type and subhalo. So we can ask the Bolshoi simulation to answer this question. And the Bolshoi simulation tells us that, depending on exactly how you ask the question, between 5 and 10% of Milky Way luminosity galaxies should have 2 such bright satellites. And then we can ask the same question in strip 82, the very deep equatorial strip of the Sloan survey. And Risa Wechsler and her students asked that question. And they tried to ask it exactly the same way. And the answer was that it seems that it's the same. So this is a nice video that was prepared by Risa and Ralph Kaler that's supposed to show the number of no such satellites, 1 such satellite, and 2 such satellites in the Sloan survey on the left and then the simulation on the right. The numbers are the number of neighbors of bright satellites per galaxy. So this is Risa's summary, and the red points with essentially 0 error bars are from the Sloan or from the Bolshoi simulation. And of course, it's a big simulation. Statistics are overwhelming. There's very little error. The black points with error bars are from the Sloan survey, which we heard so much about yesterday from Al. And as you see, every point is within 1 sigma agreement with the prediction. Now, a similar project was done, led by Eric Collerud, now finished his PhD with James Bullock at Irvine, using this time the Millennium 2 simulation. And they did something that was different. They just used the satellites for which redshifts were available. So it's a much smaller set. But they were able to construct this diagram on the right, which is the velocity offset of the satellite from the central. And what they're seeing is that the number of satellites and also the velocity offsets are in extremely good agreement with the simulation. So it looks like lambda CDM with either set of cosmological parameters is correctly predicting the number and the velocity distribution of the satellites. Now, can we turn off the lights in the front of the room so I can show some video of, thank you. So, and also these lights, if you bother to do that, thanks. So, last time when I showed this one simulation of an expanding region of the universe and the formation of halos in it was a physical coordinates visualization. But if you're trying to visualize a large cosmic region that doesn't work well. And the reason is that if you show it correctly, you have to show it so small at high redshift that this is an age of 0.5 billion years, 2.1 billion years, 5.7 billion years. And so you really can't see what's going on until it gets to be nearly the present. So what we usually do is, and also when we do the calculation in the computer, is we work in co-moving coordinates. That is, we always refer to the current size. And of course, the scaling is simply you multiply by the scale factor. Sorry, multiply by the inverse of the scale factor, which is 1 plus the redshift. So it's very straightforward to switch between the two. And you're all, I think, reasonably knowledgeable about cosmology, that you'll understand what we're doing. So now what I'm going to do is to show you the evolution of a reasonably big simulation, but this time it's going to be in co-moving coordinates. So the expansion is taken out. Now the simulation is the CLUES simulation. So CLUES is the Constrained Local Universe Simulation. It's a big project that was started by Yehuda Hoffman years ago. And the idea is that on large scales, greater than about 5 h-inverse megaparsecs, the universe is sufficiently linear that you can recover the initial conditions. So velocity data, 3 different sets of galaxy velocities for both elliptical and, so these are peculiar velocities along line of sight. Deviations between Hubble flow and the actual redshift. And there's been a series of projects to measure those. Both spiral galaxies using Pauli-Fisher relation and elliptical galaxies using something called the fundamental plane, which is an improved version of Pauli-Fisher relation, the Faber-Jackson relation. And then, in addition, X-ray cluster data was used from the ROSAT All-Sky Survey, and that was used to get masses of large regions. So all that data is used to recover the initial conditions on large scales. Now, it's not going to recover initial conditions on small scales. In particular, you're not going to, you'll, with this kind of a constrained simulation, you'll get the big things right. You'll get the Coma cluster in the right place, you'll get the Virgo cluster in the right place, etc. But you're not going to get a local group. So the rest of the game is you fill in small scales with random numbers. You do it many times, hundreds of times. You run them forward at low resolution, and you pick a simulation, you pick a bunch of simulations that look sort of like the nearby universe. In particular, you look for a local group that has the right orientation with respect to the big things like the Virgo cluster. And also, then you run those at higher resolution. You see if the local group that's in the right place also has 2 fairly massive subhalos that are in the right orientation to be our galaxy and the Andromeda galaxy. So that was done, and what we did is to run the simulation and store 7,200 time steps, as I mentioned yesterday, which is 340 terabytes of data. It's a billion particle simulation. And then we use that to get this forgot to plug in the music. We use that to get this visualization of the evolution of the simulation. Does someone know how to turn off these lights up here? You don't know how to do it? Okay, so now what's happening is we're flying through the simulation. We finished the evolution part. Thank you. And the question is, can you find the Virgo cluster and the Milky Way and Andromeda? It's in the box. So this is a 64H inverse box centered on the local group. But of course, we didn't leave the local group in the center. It's a periodic box, so you can move things around.
Okay, we're actually passing it right now. Coming next. Okay, so Mike wants to know where the "you are here" is. So there it is. So the lower one is our galaxy, the upper one is Andromeda, and that guy on the left is just an interloper. It's a foreground contamination. So Milky Way, Andromeda, and the guy on the left here is just a contamination. So let me show you the end of the last video, starting from this spot. And then you can watch as we go past the local region, and it disappears off to the left-hand side. So there's the Milky Way, there's Andromeda. You certainly get the impression that we're kind of small fish in a big pond. Okay, so now I want to move on to talk about galaxy formation. So one of the issues is that lambda CDM is a hierarchical scheme where small things form. You saw how little halos merge and merge and merge and merge to get bigger and bigger and so on. So small things form first. But that means that small structures become large structures as time goes on. However, it's well known now that in the biggest, most massive galaxies, we find the oldest stars. And in fact, we don't find any young stars. So this is a phenomenon that Len Cowie called downsizing back in the mid-90s. Massive galaxies are old, star formation moves to smaller galaxies as time goes on. So large galaxies form first, and small galaxies, at least the stars in them, form later. So isn't this a problem? Well, not exactly, because in the left we're talking about mass assembly for the halos, and on the right side we're talking about the star formation history. So the question is, how are these processes related to get the present-day structure and the current stellar population? And the answer is that there's a star-forming band. There's a range of masses where it's particularly efficient to form stars in dark matter halos. And this is something that was already pointed out in the first big paper on the cold dark matter theory, which was by Blumenthal, Faber, B, and Martin Rees, published in Nature in 1984. So this is figure 3 from that paper. And what the figure shows is that there's these black hatch things are where galaxies are. The figure is plotting velocity squared, or temperature, on the horizontal axis, and it's plotting increasing baryon density on the vertical axis, increasing downward. The curves here, these solid black curves, are called the cooling curves, and below the curve, the cooling is efficient compared to the time for gravitational collapse. And above the curve, it's just the opposite. Cooling is inefficient compared to the time for gravitational collapse. So the idea is that galaxies should form beneath the curves, an argument that was already made by Binney, by Silk and Rees, and there were 3 papers that basically made this argument. The difference was between that and the cold dark matter papers, they didn't know what the initial conditions were for forming dark matter halos. So that's what we added with these curves that go across the diagram. And that's what the cold dark matter theory gives you. So you add cold dark matter theory to the cooling curve formula, and you say that, well, galaxies should form here, and different density galaxies form in the different locations. And above the cooling curves, you should only be forming groups and clusters where the individual galaxies are down on this scale, and on bigger scales, the gas there isn't a high enough density gas to cool, because cooling is, of course, always a two-body phenomenon. Down here, cooling would be inefficient because the temperatures don't get high enough. You have to get up at least to be able to excite Lyman alpha or some metal lines. So And we pointed out that the observed galaxies all lie here. And this is basic. So these lines here, 10 to the 8, 10 to the 9, 10 to the 10 would be about here, 10 to the 11, 10 to the 12, is the mass of the dark matter halos. So the point is that where you're going to see galaxies forming is between 10 to the 8 and 10 to the 12 or so solar masses, and efficiently between 10 to the 10 and 10 to the 12 solar masses. So there's a star-forming band of masses. And halos, as they in mass, cross that band at different times. A halo that's really massive today, that's a purple curve, is going to cross that band early. And so it's going to form its stars early and shut down and stop forming stars. So those galaxies will tend to be in very massive halos, and they'll tend to have no recent star formation. On the other hand, galaxies that are just entering or just inside the star-forming band are still forming stars. They'll tend to be blue because they'll have lots of O and B and so forth stars, pumping out all that ultraviolet and blue light. And that's the fundamental distinction. And once you have this concept of a star-forming band, downsizing is predicted. It's not a problem. So this is just, you know, the tip of the iceberg of trying to understand how galaxies form. It's a very complicated process involving gas cooling, gas reheating from star formation, from the energy that's released as things fall into supermassive black holes, and all of that has to get included. And now we know that the arguments that we gave back in the 1984 paper were incomplete in that they didn't include all of these different phenomena. Another phenomenon that's been appreciated for the last decade or so is something called cold flows. That gas tends to come into dark matter halos along filaments, and at least until the mass of the dark matter halo exceeds about 10 to the 12 solar masses, the cold gas can reach close to the center and directly form a disk and bring in a lot of angular momentum. So these are all phenomena that need to be included in semi-analytic models. These are models that simplify galaxy formation mainly by making it always a one-dimensional process. Everything is sphericalized. So there's a lot of linear differential equations instead of the complicated nonlinear and three-dimensional partial differential equations that really describe what's going on in galaxies. So the idea is you run enough high-resolution simulations to try to abstract the key ideas, and then you try to summarize them in semi-analytic models. And there'll be much more discussion of semi-analytic models, especially by Darren Croton and others. So this is the basic idea of semi-analytic models. Gas cools, makes disks. There's another one. This one falls into this one, becomes a subhalo. It can merge with the central object. That can produce a big burst of star formation. It might fuel an active galactic nucleus. Finally, this halo is too massive to form stars efficiently, and it's an old red dead galaxy, whereas these are blue star-forming galaxies. And all of these different phenomena have to be included, including AGN feedback, something that was included as a sort of continuous process first time in Darren Croton's semi-analytic model based on the Millennium simulation. He called it radio mode feedback, and all successful models of knowledge include that. That's crucial to having these old red dead galaxies. You also have to include the effects of dissipation in gas-rich galaxy mergers, and this, as my former student Matt Covington and now continuing work by Lauren Porter showed, leads to a very good agreement in the steep size-mass relation for elliptical galaxies and also the small dispersion that's observed. That is, it's a tight correlation between size and mass of elliptical galaxies. And the semi-analytic models that didn't include dissipation do a very bad job of this. And we showed that it works, and then another semi-analytic model led by Shankar got the same results we did. I think it's guaranteed that you'll get good results if you include this, and we give a simple model for doing this. And then you have to include spheroid formation by disk instability in order to reproduce the observed elliptical luminosity function. And these are some of the key papers, including a paper that Lauren Porter is going to resubmit soon to monthly notices. And the referee will surely accept the revised version. The referee is herself one of the big experts in doing this kind of work. Guinevere Kaufman, who was the first author of the first really detailed semi-analytic model, along with her husband Simon White and one other co-author, Bruno Guiderdoni. So this is the result of Lauren's latest work. So this is a comparison between Jenny Graves' summary of the galaxy age on the fundamental plane. So in the fundamental plane, if you look at the face-on fundamental plane, this is the velocity dispersion of the elliptical galaxies, and this is their size. And same thing, except now what we're plotting, here we're plotting age, and this is the log of the age, and the oldest ones are red, and the youngest ones are blue. And this is a very similar diagram, and the part that corresponds to the observations, where they had enough data in Sloan, is always shown in this dashed curve. And the general trend, which is that there's very little dependence on radius and strong dependence on sigma, appears to be reproduced. This is two different kinds of metallicity tracking iron group elements and alpha elements. And again, roughly speaking, trends are reproduced, although here we may be seeing a little bit more dependence on radius than the observations indicate. But the semi-analytic model is tracking 12 different elements using type 1a as well as type 2 supernovae. And this is the kind of thing that more and more is going to be expected for semi-analytic models. And of course, what we're looking for are the discrepancies. Now, the model is carefully tuned to match the low resolution universe. Sorry, the low redshift universe. So an interesting question was, how does it do if we instead look at the latest data coming in on high redshifts? Most stars form at redshifts between 1 and 3. That's high noon for star formation. And fortunately, with the new wide field camera 3 on Hubble Space Telescope, which goes out to 1.6 microns, H-band, we are now getting beautiful images of galaxies in optical light, that is the light our eyes see, out to redshift 3. At redshift 3 we can see blue light. At redshift 2 we see the entire spectrum using the currently available cameras on Hubble. And the Candel survey, led by Sandy Faber and Harry Ferguson, got the great prize of the largest allocation of Hubble time ever, over 900 orbits. We're getting something like 10,000 galaxy images per month that we couldn't get before from Wide Field Camera 3 for 3 years. And using this, we have learned a lot of interesting things. This is from a paper that was just submitted a few weeks ago. So basically what this paper argues is that there's two different tracks for evolution of galaxies. The horizontal axis is slightly weird. It's the surface density would be the luminosity divided by radius squared. This is a kind of a reduced surface density. It's divided by radius to the 3/2. So it's luminosity divided by radius to the 3/2. And the reason is that that basically is the scaling relation for elliptical galaxy size-mass relation. It works at all different redshifts. So if you want to compare different redshifts, that's a good thing to use. And so the left-hand side is low surface density. The right-hand side is high surface density. The vertical axis is specific star formation rate. Star formation rate divided by stellar mass. So the upper part is galaxies that are red and dead. The lower part is galaxies that are still forming stars. So to summarize, this is diffuse star-forming galaxies. This is compact star-forming galaxies. This is diffuse quiescent galaxies. This is compact quiescent galaxies. Now, the paper argues Now we actually can follow populations of galaxies from Redshift 3 down. The paper argues that there's two different tracks. We're calling it the fast track and the slow track. I convinced them to use that terminology. And the fast track says that you very quickly go from diffuse star-forming galaxies to compact star-forming galaxies, and then very quickly go compact quiescent galaxies. So big blue galaxies become blue nuggets, which quickly turn into red nuggets because the star formation is terminated very quickly. A large fraction of these galaxies have active galactic nuclei in them, quasars or other bright. The ratio of active galactic nuclei here to here is 30 times more per object here. So this is where we're getting the active galactic nuclei. And one possibility is that you're going from here to here largely by major merger. That's not what the semi-analytic model says. It says that disk instability is also relevant. So the question that Lauren Porter addressed was, okay, take the same semi-analytic model that agrees so well at low redshift with the observations of Sloan. How does it do at redshift 2 to 3? So there's the result. So this is, again, from the paper. And this is that same diagram. And this shows how you have this population of the star-forming diffuse objects, the star-forming compact objects. The stars are the active galactic nuclei and quasars. And this is at redshift 3 to 2.5, 2.5 to 2.2, 2.2 to 1.8, and so forth. And what you're seeing, if you look at this carefully, is that you're at low redshift getting essentially none of these compact star-forming galaxies, and also very few compact quiescent galaxies. And instead, you have a population of diffuse star-forming galaxies and diffuse, that is not so compact, quiescent galaxies. But at higher redshift, you have these striking compact ones. So this is what the semi-analytic model says. And it's not getting them to be as blue as the bluest ones observed. Of course, part of that could be contamination from the AGN. But the basic trend was sufficiently similar to the observations that I think it's fair to say that when Lauren showed this to the observational team in Santa Cruz, their jaws dropped. No one expected that the model would do anything like what we saw. But as you see, it does. And why is it doing this? So Lauren made this picture that actually shows how the population evolves. The blue are gas-rich mergers. The red are gas-poor mergers in the last gigayear. And so you can see the great thing about semi-analytic models based on a merger tree is that we actually can follow every individual object, every halo, as the galaxies evolve. We know where they are. We know, if we're looking at a galaxy at 1 redshift, what its progenitors were and what it's going to turn into. To show this both as an amazing illustration of how well this approach seems to be able to capture what's going on, and also illuminate, because there's a significant fraction that did not form by gas-rich major mergers. But they did do this track of going from the bottom left to the bottom right and then up. Okay, well, I don't have much time to talk about hydrodynamic galaxy formation simulations. I just wanted to mention that you have to take dust into account. This is the famous antennae, 2 galaxies that are passing each other and are eventually going to merge. Their centers are going to merge. The region where most of the star formation is this region here, which is pretty dark in the optical, and that's because there's a huge amount of dust which is absorbing most of the light. But if you look in the infrared, that's where almost all the energy is actually coming out. So dust can easily absorb 90% of the optical light in regions that are densely forming stars. The Sunrise Code by Patrick Janssen, former graduate student and postdoc with me, is the best code available for capturing this. It's a ray tracing code. It's 3-dimensional adaptive grid. It takes into account in a simulation where the gas and in particular where the metals are. You can make different assumptions about the size distribution and so forth of the dust grains, and we are typically tracking 100 or several hundred wavelengths simultaneously. We carry a vector of wavelengths and change the probabilities, and so it's possible to do many wavelengths simultaneously, including, incidentally, lots of the favorite lines that observers use. And we showed that graphic processor units give a factor of 10 speed up. So this is an example of the kind of spectra that come out of this sunrise calculation. Blue without dust, we always calculate without dust. Face on and edge on, because of course we can calculate what the things look like from every perspective. Chris Moody has become the expert in running this. So this is an example of a galaxy merger simulation where we've used 3 colors to give you a sense of what these things would look like to the eye. So this is a collision between 2 galaxies the size of the Milky Way and Andromeda. Lots of star formation. So I hope you appreciate that for every one of the thousands of images you're seeing, 30 times 30 images a second, we had to run sunrise. And see those beautiful dust lanes? Now the centers are merging. So this is a gadget calculation that was run by Greg Novak. Patrick Johnson did the code, the sunrise code. And this and many of the other visualizations I've shown you are on that website, new-universe.org. And they're also going to be on the gallery, which will collect lots of these visualizations, at hipac.ucsc.edu. So now we're just rotating around the galaxy. Incidentally, we see lots of elliptical galaxies with these big dust lanes. So when the universe is twice its present age, the distant galaxies will have disappeared over the cosmic horizon, and Milky Andromeda, or whatever you want to call the combined galaxy, will be all that's visible in several tens of billions of years. Mike Busha and his thesis work at the University of Michigan did a simulation that he carried into the far future. And that's what the local universe looks like in 80 billion years. Pretty lonely. And this is just a summary of this paper that Patrick and I published a couple years ago, where we explained the code, the CUDA code, that allows us to get this tremendous speed up of this particular kind of calculation using graphic processor units. Rocha was here yesterday. Are you here? Yeah, good. Okay. So Miguel Rocha, as a senior thesis student, and then continuing on for a little while at Santa Cruz, led this paper where we actually showed what was the right metallicity gradient with Redshift to reproduce the observed metallicity of spiral galaxies as a function of radius, the color distribution of spiral galaxies as a function of radius. We did many, many simulations using sunrise. We looked at them at many time steps, and we measured what we call the observability timescale for various indications of merging activity. What it will give you is always just number counts of objects in a given region of the sky, objects that satisfy certain criteria. If you want to get a rate for things like mergers out of that, you have to have a time scale. And in particular, the time scale you want is this observability timescale. So using the observability timescale, first we had to do many papers where we laid out in detail how we calculated observability timescale from these realistic simulations. But then we took all the available data and combined it together to make real measures of the merger rates, gas-rich, gas-poor, major merger, minor merger, and we compared them to available semi-analytic models and Kyle Stewart's low-resolution hydrodynamic calculation. And the results actually were really pretty good. And in particular, many different groups had claimed very different rates And it turned out that they were just making different assumptions about observability timescale, which were not based on anything. So I think this is a really important paper led by Jennifer Lotz, who started this project when she was a postdoc with me at Santa Cruz. This shows this cold flow phenomenon. So this is an example of hydrodynamic simulations that we're running. We've run many dozens of these. There's something like 40 actually running right now on supercomputers at NASA Ames and Lawrence Berkeley Laboratory. And these are visualizations. The white stars, the blue is gas, and of course different colors correspond to different densities. These are, so every 100 million years or so, that's about 100 of these visualizations for a single forming galaxy. We run Sunrise on this. This is Chris Moody's project. And this is simply looking at what these things look like. This is very preliminary, but it's just to give you an idea. We're currently storing something like 2 terabytes of output from the running simulations every day, because we're storing every major time step. Far more than we could ever look at. But when we see that interesting things are happening, because we're also running merger trees on the underlying dark matter in the simulation and also on the stars. So when we see interesting things are happening, we can then go back and we can actually look at exactly what's happened. This is showing some of these simulations. The simulations are being run mainly by Daniel Severino, who's now in Madrid, his hometown. He did his PhD and developed techniques with Anatoly Klipin at New Mexico State. So these are, on the left, observed Redshift 2 galaxies, simulated, of course, chosen to look as much as possible like these. This is the same galaxy. This is gas, face on, edge on. This is a blow up of this region. This is the region surrounding this galaxy. And here what we're doing is poking lines of sight through it, background stars. And this was led by Michele Fali and Jason Prochaska, who are great experts in doing this. So they basically used our simulation as a laboratory, and the conclusion was that it really looks a lot like the distribution of different density gas, damp Lyman alpha, the Lyman limit systems, and so forth that we see in the real universe. This is the Candel survey. It's the largest project in the history of Hubble, and what you're supposed to appreciate is that the top is showing you these H-band images. The bottom is what we had to work with before we had wide field camera 3. That's the image from advanced camera for surveys. And I hope you can appreciate having the optical images of the galaxies in the rest frame makes a huge difference. And having all of the different wavelengths makes a huge difference. So this is an example of how we add dust to the simulation. This is without dust. This is what dust does. It tends to obscure these star-forming clumps. And then it looks a lot more like the real images. That's V-band on ACS. That's H-band. And of course, we have all the images to work with. So the idea is that we can use the simulations to understand what's going on. So this is the big questions that we're trying to answer. The nature of dark matter, the nature of dark energy, which of course determines the future of the universe, the early evolution of the universe. Of course, that picture I showed from Mike Bush's work, that's assuming it's a pure cosmological constant. If it's not, the future could be very different. And the only way to find out is to study the past very carefully. Formation of the first tiny galaxies and the first stars, how the universe reionized, how the entire population of galaxies forms and evolves from direct observations from the ground and space, interpreted with the help of simulations, including star formation feedback from supermassive black holes, etc. So these are the big projects in at least understanding the evolution of galaxies and the nature of dark matter and dark energy. One last thing, I want to take account again to see how many people want tickets, want to go on the excursion on Sunday. Richard III have a whole afternoon in Balboa Park with lots of interesting things to do, and a stop on the way at the Birch Aquarium, and also a fancy dinner at a restaurant in Balboa Park. So last time there were a total of 32 people please raise your hands. And if there's more, I want to be able to get the right number of tickets. 1, 2, 3, 4. This time I just got 29. Okay, so 30. So I think what I'll do is get 32, just in case there's a couple of people who aren't here who might want to go. And then we'll surely have enough. And also, the largest bus holds 36. So if a couple more people want to come, we can certainly accommodate them. Okay, sorry to run a little bit over and cut into my... Yes? Yeah, lots of simulations have considered alternatives to just a cosmological constant. Mike Coulin ran a series of 6 such simulations in a project with me, and that was published like 4 years ago. And many, many other people have done such calculations. Never, I think, with the kind of massive computer power thrown at it that we did with Bolshoi. But the bottom line is that if you assume, well, actually, let me take other questions. But there's a very, you can ask me privately, there's a very simple back-of-the-envelope calculation that actually captures the key thing that happens. Basically, what you're doing is you're controlling when halos form. And that then controls how galaxies form. And it's a very simple thing to calculate, and the Coulin detailed simulations basically showed what we expected. Another question? Yes?
So at the beginning of your talk, you mentioned how Bolshoi and the Millennium Run use different values for cosmic parameters.
Yes.
What kind of difference did that make in the result?
It's a complicated question. So the question was, how much difference does it make in the results, whether you use Millennium or the Bolshoi simulation? So there's a new paper that just came out that I haven't had time to fully absorb by Guo, White, et al. And Gerard Lemson is a co-author on the paper, so he may be able to clarify this. There was an earlier paper by Guo, White, et al., which was a semi-analytic model. This new paper is also a semi-analytic model. The new paper addresses this question because they used a method due to Anguillo and White to try to rescale the Millennium simulations to the correct cosmological parameters, WMAP7 cosmological parameters. And what both papers agree on is that, at least one of the things they seem to agree on, if I've correctly understood the new paper. I was the referee of the earlier paper, so I understand that paper in great detail. But the new paper seems to be saying the same thing. So the biggest discrepancy, or a very big discrepancy, between the real universe and the Millennium simulation, where the halos are filled with galaxies in a physically reasonable way, was that it is significantly over-predicting the abundance of pairs of galaxies of, say, Milky Way luminosity or less, lower luminosity, at separations of about a megaparsec or less. About a factor of 2, higher two-point correlation function at a scale of 1 megaparsec, even higher, factor of 4 or 5 higher, for smaller galaxies at smaller separations. The simple explanation for this is that the two-point correlation function is simply counting pairs. Most of the pairs on those small separations are going to be within a single halo. It's what we call the single halo term in the halo occupation distribution formalism. And if you have too many massive halos, which you're going to have if you have too high a sigma 8, you're going to overpredict the number of such pairs. And as far as I can see, both, certainly the original Guo White paper said that that was the explanation for why they were getting this. Gerard, is that seems to be consistent with what the new paper is also saying. Certainly the new paper says that it's seeing the same phenomenon. Right, when you even, no, what the new paper says is that the WMAP7 doesn't have this problem, but the WMAP1 does. Okay, anyway, so that's an example of the sort of thing. The new paper says that the combination of Well, the WMAP 7 results and the WMAP 1 results, the original Millennium results, are actually surprisingly similar, they say, for the mass distribution of halos at fairly low redshifts. And I wouldn't know, because we only did Bolshoi. However, let me make a general comment. It's really useful to have high-resolution simulations with different cosmological parameters, because one of the jobs of the next generation of surveys, like the Dark Energy Survey with the Blanco telescope at Cerro Tololo in Chile, is going to be to try to measure the cosmic parameters, and in particular, the things that are connected with dark energy, with unprecedented precision. And then LSST and Euclid, and if possible, the spy satellites that were given to NASA and could be turned into fabulous W-FIRST type satellites, if NASA's willing to spend another $1 billion or so. The whole challenge is to measure these cosmic parameters with extremely high precision to try to determine the future history of the universe by measuring very carefully the past. So it's critical to have different simulations to test the ability of observers to tell the difference. And Risa, I think, is going to explain in some detail how the Dark Energy Survey project is taking up this challenge. Any other questions? Yes?
What about the numerical simulation to producing downside?
I'm sorry, what about the what?
Numerical simulation to producing the downside.
Oh, the numerical simulations, as long as they capture this physically very reasonable phenomenon of having a star-forming band of masses from around 10 to the 10 to 10 to the 12 solar masses, they'll automatically reproduce downsizing. It's not a problem. It happens in any simulation that has the right physics in it. Another question? Miguel?
About Lauren's work in semi-analytics, you mentioned merging as one process for going from diffuse star forming to compact star forming. What other process? You say that not all of them merge.
Yeah, so the other process that Yuval Birnbaum and Avishai Deckel and also Dushan Karas in his thesis work emphasized almost a decade ago is an instability. So the cold flows feed disks, and they can feed the disks with so much gas that the disks become unstable. In the centers, they become very dense and unstable, and they form bars, and that can drive gas into the center. Also, the disks can become unstable at larger radii and form giant star-forming clumps. You saw some of those in the simulations, and also in real galaxies. And those will tend to flow into the center by dynamical friction and also viscous processes. And so what that can do is, on a time scale of about half a gigayear, that can greatly reduce the physical size of the stars. And the question is that fast enough? Because the evidence that we're getting from the Candel's observations is that that may not be fast enough. Because we're seeing this very rapid transformation, and moreover, this very high probability of having active galactic nuclei once you get into this compact phase. So a very interesting question is going to be to really clarify what the speed of this is, because that's going to be critical, because the mergers do it very fast, on a scale of about 100 million years. Can the disk instability get it fast enough? And the answer is, I don't think we know. That's going to be a really interesting question. I think we've really run out of the question time. Yeah, one more. Yes. We're just looking at, oh, I see, you're saying in the semi-analytic model. Lauren?
Sorry,
well, all the progenitors, see, what we're doing is we're checking what's actual galaxy at any given time. So that includes all of the smaller progenitors, because they're now in the galaxy. So I think the simple answer is yes. But for more details on exactly how it's done and lots more illustration on her, I mean, Lauren has all these results on her laptop. So raise your hand, Lauren, so everybody knows who you're talking. Okay, so just ask Lauren. And of course, Darren Croton will have a different take on these same questions because he's running semi-analytic models. And Risa Wexler's postdoc, Yu Lu, also has a semi-analytic model. Those are the three groups that have had access to the Bolshoi merger trees for months now. They're now public. They're going to be available here, and they're going to be available to the world. So we're hoping that lots more people start to use them and let 1,000 flowers bloom. It's time for a break.